Okay, so got a man pulling a boy up on a tree as shown here. Okay, he's walking backwards, right, at 1.5 meters per second. Okay, and I want to find the speed of the boy as he moves up at an instant when xa equals 4. Okay, rope is 16 meters long. So again, what we're going to do is we're going to write the length of the rope here. Okay, which I know to be 16. So we'll start with that. So 16 equals, okay, so, and I want to write this as arbitrarily as possible. So what I have, if I start at B, as shown there, I've got YB, right? Where that's basically the position of the boy. Now, the thing that I need is the length of the rope, the straight line distance from A to C. And what I've got is a Pythagorean theorem idea here, where I'm going to take, okay, the square root of x a squared, right? The distance of that side of the triangle, and then the distance of the other side, which will actually be 8. You might think it's YB, but remember, that guy isn't moving up with the boy. He's at a fixed distance below the branch of 8 meters. So it'll be plus 8 squared. And that 8 is going to remain constant as he moves backwards, right? He's not moving up and down. He's at a fixed height, 8 meters below that. Okay, so that I'm going to write just a little bit differently when I write it over here, and that's going to be x a squared plus 64, that's the 8 squared, okay, to the 1/2 power, which is how we write square roots. Okay, so now I'm going to take a time derivative of this guy. Okay, so again, 16, the length of that rope does not change. It's going to hang out at 16, or at 0. Yeah, it's going to hang out at 16, so the time derivative, its change in length as a function of time is 0. Okay, yb goes to yb dot. We're going to do it that way. Okay, now I need to take the time derivative of this. Okay, now, okay, I have to take the derivative of the inside times the derivative of the outside. Okay, so let's take the derivative of the inside. Okay, 64 is 0, so I've only got that x squared. However, it's x squared, which I have to write as 2x dot times x. Okay, the other way you can think about it is, if I've got x times x, I'm going to have x dot times x plus x times x dot, which is 2x dot x. Okay, so that's the derivative of the inside. And then I've got to take that times the derivative of the outside. I'm going to bring down the 1/2, and then I'm going to take x squared plus 64, and then this goes to the negative 1/2 like so. Okay, so that is the time derivative of the length of that cable. Okay, so what I need to do here is, again, what am I trying to solve for? I'm trying to solve for the velocity of B, which is yb dot. That's what the boy is, right? So I'm going to solve for velocity of B, which is yb dot, which is going to be negative 2 times x dot, which is 1.5. Now, x is going to increase, so that 1.5 is going to be a positive value, right? As he moves what we think of as backward, xa actually increases in size, so we're going to call that a positive velocity, okay? xa is, I want to find this when xa equals 4. Going to take that times a 1/2. Then on the inside, I've got xa, which is 4 squared, plus 64 to the negative 1/2, like that. So from that, I can find the velocity of the boy, just solving that out, and I get a negative 0.671. And what that negative tells me is that YB is shrinking, which means he's moving upwards. So again, positive and negatives are all based on where your your 0 point is, and think of it more as, is it increasing in length or decreasing in length? And YB is decreasing in length. So that's why we have a negative on that one. So again, you just write the equation for the cable and then take a time derivative knowing that that length cannot change with time.